Hey everybody, today we're going to talk about backpropagation, and you've already gone through some background on forward propagation, so you understand some concepts about inputs and multiplying the input times the weight gives you an output. What we're going to do today is talk about backpropagation, which is one of the topics that kind of trips students up. To really understand this concept, you kind of have to dig one layer deeper, and we're going to do that today, but we're going to also keep it simple and have the simplest model that we can talk about. I don't think it's complex from a mathematical perspective. I think it's complex from an accounting, all the variables and making sure that you have everything just right. So let's go ahead and dig into this. And the first thing I'm going to do is just draw a model for you of what we're trying to do. So a simple model is we have an input. Oops, let me turn on my pen. We have an input, and we're going to call that I. And then what we're going to do is we're going to feed that input into a neuron, and we're going to call that output. And let's go ahead and just say this is our output, and this is our input. And what we need to understand what to do is how to change W to really make our model work to achieve the desired output. So remember that W is randomly assigned in the beginning, randomly assigned. And I'm going to switch to a little bit thinner of a pen so we can do that. So let's make a table so we can keep track of how we change these things in our variables, because this is all about accounting. So our input is I, and then we have Y, and let's just go ahead and make sure we really understand. That's our desired output, okay? That's our target. And then we're going to also have a calculated output, and let's give that the variable name A. So if we made a little table here, it looks something like this, okay? And so we're going to take our simple neural network and do some calculations. Now, let's remind ourselves that the output, our calculated output, A, is equal to W, the weight, times the input. So that's one thing that we know already from our forward propagation. So really, the challenge for back propagation is what is the next W. So that's really what we're trying to figure out here. So let's do that. So let's introduce some definitions here. If we were to come up with a way to calculate the error, and we were to call that, and it's called this in your Keras machine learning library or module for Python, it's called the cost function. So that's just another definition that you should be aware of. So error is the cost function. Let's call that C. And so if we came up with a definition for our cost function, C, let's use just A minus Y squared. So that's error squared, okay? So A is our calculated output, Y is our target. We subtract those and square them. So if we did that for our current values right now, so A, let's define our input as having a value of 1.5, and then our desired output, let's say, is 0.5. So what would A be? So A is W times I, so let's just go ahead and write that here. A is W times I, and W is, let's assign that as a value of 0.8 to begin with. Okay, so 0.8 times 1.5, so that's 1.2. Okay, so if we knew that we did 1.2 minus 0.5 is our target, that's 0.7 squared, that's 0.49, we're about 0.50. Okay, so we know that we're off, we're above where we need to be. If we need to be at 0.5, we're at 1.2. So we know we probably just intuitively here, we need to change our weight, we need to go down on the weight. So how do we do that? What's the process for doing that? So I'm going to introduce the idea of gradient descent, and draw you a diagram so that we can walk through this. So gradient descent basically is, and if we take our cost function, this is our cost function. So we're applying a gradient descent to a cost function. So this is C. Remember that C is A minus Y squared, and then on the x-axis we have A. So if we were at 0.5 A, we would have a 0 cost function. So that's our goal. And if we drew this function, it's a parabola. So I'm going to try to draw a parabola here. So we have a parabola that looks something like this. And then the crossover point would be what? If A is 0, and Y is 0.5, and this would be 0.25. It's a symmetric function. So this is A of 0.5, so this gives us a 0 cost function. And then over here at 1 minus 0.5, that would give us another 0.25. All right, so where we're at right now is 1.2. We're up here somewhere, right? So 1.2. So we need to do we need to perform a derivative. Derivative is the slope of this to tell us what direction to go. And if the derivative is positive, then we know we need to go in, we need to step in the negative direction this way. Okay? So you guys have done a lot of math at this point. And so bottom line, if we have a positive slope, we need to do the negative of the derivative. And if we were in multiple dimensions, we would say we need to do negative of the gradient, right? This gradient could be multiple dimensions, x, y, and z. Right now we're just looking in one dimension. So we need to take the negative of the gradient, or in one dimension, that would be dc over dA, right? That's the slope of this line right here. Boom. So we need to take the derivative of c with respect to a. So let's just go ahead and calculate that. dc over dA is equal to, and here's our c function over here. You should be able to do this off the top of your head. dA minus y. All right, so that's dc, and so that's c is a function of a, right? That's what this is. C is a function of a. Okay, so really, we don't really, we need to know the direction of this, but we really need to know how to change c with respect to w. And we just calculated how to change c with respect to a, but we need to know how to change to make it with respect to w. So I got to introduce a new concept called the chain rule. Now you guys have done the chain rule in your calculus class, maybe even your vector calculus and differential equations. And if you remember the chain rule, it's got a pretty simple definition, but it's a lot of words. So let me just write this out. It's the rate of change of a function of functions is the multiple of the derivatives of the functions. All right, that's kind of wordy, derivatives. So if we were to write this mathematically, you guys have seen this before, right? So that's a lot of words. If we write it real succinctly, partial of f over the partial of x, and then f is of another function, right? G of x is equal to, and what I just said was, okay, it's g of x times f of g, the derivative f prime of g. So really what we're saying, we're going to take these two derivatives, and that will give us, that's the chain rule, and that tells us the rate of change. Now, that's a little bit complex, and I think I have a simpler example that I always think about with what we're dealing with here is, and with the chain rules, if I told you that that a train is 2 times faster than a horse, and Usain Bolt is 2 times faster than or 3 times faster than a train, right? So I said this was 2x and this was 3x, and I said, well, how much faster is Bolt than a horse? You would know, just intuitively, you would know it was 6, right? So what we just did was g prime of x dot f prime of g, right? You with me? So basically, if I told you train is 2 times faster than a horse, and then Usain Bolt is 3 times faster than a train, you just multiply those together and get 6. So we all know that intuitively, but that's the chain rule. That's a very simple way to think about the chain rule. So really how that applies to neural networks, if we come back to a neural network, we need to know the change in the cost function as a function of the weights, and we need to back propagate that if we had multiple layers. If we had another layer out here, we would have another W here, and we need to back propagate that through our particular network. So let's call this the last layer, layer 2, and the first layer I just talked about, layer 1, okay? And let's go back and clean this up a little bit. Let's go back and then kind of relate this back to the neural net. And it's kind of a simple way to think about this from a Usain Bolt and trains and horses is if I had partial x and I wanted to take the derivative of this and just relate back to what I just talked about, is conceptually we have layer 1, or layer 2, excuse me. The last layer is layer 2. We need to make the derivative of that guy. And then we need to take the derivative of layer 1. And basically that's what we talked about from a conceptual perspective. And this becomes, what's the partial of layer 2 for partial x dot layer 1 over partial layer 2. So what's the change in each layer, right? And so this is a way to conceptually think about it. We're just back propagating by looking at the derivatives of each of these layers. Pretty cool, huh? All right. And so a conceptual way for you to think about this. All right. So what we need to do now, let me come back to the problem at hand. We found dc over dA here, but really what we need to know is dc as a function of dw, all right? Because we want to know how to change w and relative to c. So the equation for that is if we have the new w, new 1 is equal to w naught minus something called the learning rate and then the cost function with respect to w, so dc dw. So the question becomes, how do we calculate dc dw? All right, well, let's get after it. Let's do it. So the way to do that is, if you think about this, this becomes, using the chain rule, partial c over partial w is equal to dA over dw dot dc over dA. All right, so this is the chain rule once again right there, okay? So remind you what our model is. Here's our input, and our input, remember, it was at 1.5, and then we were trying to figure out the new w, and then A is equal to IW, and then we know that the actual output, or the desired output, is 0.5, and our initial W was 0.8, all right? So W naught was 0.8. So let's go through the calculations here. So WC, or DCDA, is equal to, remember, 2A minus Y, right? And that is equal to 2IW minus 0.5. All right, if we do all the calculations, we calculate this out. This is equal to 3W minus 1. And then we need to know DC to do the chain rule up here. We need to know DA, let's see, DA dW, and that is equal to I. If we did the derivative of A, right, or A with respect to W, and we know that A is equal to WI, then the DA dW is equal to I. So that is equal to 1.5. So if we now do the calculation of what dC dW is equal to dA dW dot dC over dA, it all becomes really clear. This dA dW is I, which is 1.5, and then we did the calculation before that 3 dC dA is 3W minus 1. Oh my gosh. All right, so we have had to keep track of everything here, and bottom line, this becomes 4.5 W minus 1.5. All right, so, and now we need to change the next W1, the next weight is equal to the original weight minus something called the learning rate times dC over dW. And so we just calculated dC dW, which is 4.5 W naught minus 1.5. And let's go ahead and do that. And now we have this new concept called the learning rate. So here is called the learning rate. And Keras, it's also referred to as alpha. So this is our learning rate. Now, so the way to think about the learning rate is that we're using this derivative, and then we're multiplying this dC over dW by a certain factor. So if we multiplied by a lot, let's say if we have a big number, we can boom, go over here. And then another big number, if we really tried to do this, we could go back and forth like this. What we want to do is really take a small step and a small learning rate and converge on our answer, which is 0.5. So really this learning rate needs to be fairly small, and we're going to initially right now say it's 0.1. Usually that's pretty big. Just for our calculation purposes, we're going to use 0.1, but in your machine learning models, they may be 0.001 or even smaller, okay? So let's plug this in. I believe to begin with, this was 0.8. This was 0.1 is what we just said. And then this is 4.5 times 0.8 minus 1.5. Okay, so we've done a little bit of work here. And so some key things to point out here is that we were going negative to the gradient, right? We knew that if the derivative or the gradient was positive, we need to go in the negative direction. And if the derivative is negative, times a negative, then we need to go in the positive direction. You can see that on our graph. So if we were on this side, we'd be converging this direction, right? We'd be coming down this direction from the slope. If we were on the other side, we were high. Okay, so that is a conceptual overview of backpropagation. Now, we did it just for one node. Imagine if we have many layers and thousands of nodes, keeping track of all these variables is really a daunting task. That's what Curious, really the machine learning libraries and functions do for you, is they track all these things. So we need to know conceptually how they work and how to optimize the parameters, but really that's what's happening in the background. Now I'm going to cover this in some Python code. It'll be good review for you for the Python code, but ultimately I think at a high level this covers the concept of back propagation. All right, until next time, regards.